Hi everyone, this is Blaine, professor in Chem 112, talking about week 7, HPLC, talking about the instrument and analyzing its results. Take a look at the instrument here. It's very similar to the two that we have in our lab in Chem 112. It is the same one. Take a look up here, you'll see the mobile phase. These are the buffers that we use to run our samples through the system, through the column here. For our Benadryl samples, we will be using the phosphate buffer that you guys made earlier a few weeks ago at this point. Those buffers are pumped into the column via some very strong pumps housed here in this location. And then the auto sampler, which houses our samples, is right here. You guys remember that tray that you put all those glass vials in last night? That's where the auto sampler is. It has a little robot arm and a needle that takes the solution out of the vial. The column, if you guys have walked by the HPLCs in lab, you probably saw a metal column attached to some tubing. That's right here. We'll talk a little bit more about that here in a second. And then the UV spectrophotometer is down here. Sure, we can run samples through the column, but we do need to be able to measure how much of our samples we have. That's where the UV spectrometer comes into play. It's not too different from the spectrometers you were using a few weeks ago. Of course, that's connected to the computer where we can see our results, and then the printer where we can print those off. So just to visualize the process, what it looks like, I've got a couple of videos I'll show you here. This is what the auto sampler looks like. Here is the tray with all your samples on it. What happens is a robot arm comes around, picks up your sample, takes it over to the side, and as you can see, a little needle injects in there and starts pulling out some of the liquid. The robot arm will then return your sample to the tray, just like you saw it where you put it. This is an example of what the UV detection looks like. As you can see, these little white spheres are representative of the solvent. This line here. But as you can see here, this is what the chromatogram looks like. The solvent doesn't register any absorbance because we zeroed the absorbance for solvent. But when these green spheres, which represent your sample, when those enter past the UV vis spectrometer and the detector, you'll note that a peak starts forming on the chromatogram. More solvent, so zero absorbance, and then sample starts coming in, these red spheres. That represents a peak. There's another video here which more explains what I'm going to talk to you about here in a second about the column and how it works. Go ahead and feel free to take a look at that. It's got someone explaining the process, which is why I don't really want to play it now for you. So what does it look like inside the HPLC column? It's a stainless steel tube which is packed with tiny particles. Those particles are made of silica, and they are super, super tiny, smaller diameter than a strand of human hair. The column we used to measure our headache powder, as I mentioned earlier, is a carbon-18 column. That carbon-18 is a very, very greasy substance, very, very non-polar, meaning if we were to put some of that substance in water, it would not dissolve. So our aqueous samples are going to travel through this carbon-18 column, passing through these little channels here. The non-polar substances are going to want to stick to that column, whereas our polar substances are going to want to get out of there fast. We'll talk a little bit more about that here in a second. As you can imagine, it's going to take a lot of pressure to push the mobile phase through the column, which is why HPLC stands for high pressure liquid chromatography. You'll also see it called high performance liquid chromatography. That's because with some columns, high pressure isn't needed. So they just wanted to change the acronym up and confuse us just a little bit more. So why do we use this column? The column is going to help us to separate our compounds. In the case of the headache powder, it's going to help us separate the 3 active ingredients that comprise the headache powder. This separation is based on polarity. HPLC is able to separate based on other physical properties, but in our case, it's separating based on polarity. In our case, the stationary phase, that greasy carbon-18 column, is nonpolar. And then what kind of compounds are attracted to that stationary phase, polar or nonpolar? So you guys probably learned in your first chem class that like dissolves like. In this case, it's the same. Like also enjoys being with like. Nonpolar wants to associate with other nonpolar substances. Nonpolar and polar just don't mix very well. When you guys take a look at your Italian dressing, you'll see the oil has separated from the water. That's because the two don't like being together. So, the most nonpolar compound in our samples is the one that's going to stay on the column the longest. It's going to have the highest retention time, meaning it's going to spend the most time being retained on the column. The most polar compound is going to have the shortest retention time. It's going to want to get away from that column. So, let's talk about those chromatograms that I passed back last night. Each student should have a standard chromatogram for all 3, aspirin, acetaminophen, and caffeine. You should have had 1 that you did yourself and should have gotten 2 from the other students that you partnered up with. A big thank you to Dr. Galbraith for making those copies for us. So, you guys should see on the top of those chromatograms the name, but go ahead and write out in ink on top of the peaks standard acetaminophen, standard aspirin, standard caffeine, and then go ahead and also write the concentration. Excuse me, because that will be useful to us when we do our calculations later. Each student should also have an unknown chromatogram, that is the headache powder. We'll talk a little bit about that as well. Make sure that you're not confusing these, which is why I want you to write their names where you can see them most easily. And then as we do our calculations moving forward, make sure that you're holding on to all significant figures and units unless I tell you otherwise. So if your HPLC were printed in color, it would look something like this. You would have a blue peak, and then the pink line is something that we add ourselves. Go ahead and add that to your chromatograms right now. Pause this video for a second and do that. This is going to help us to calculate peak area later on. Your chromatogram should be very, very, very flat, except for these peaks here. In this case, we would have had pink highlighters to put a nice flat line, but unfortunately you guys are missing out on week 7. So go ahead and look at your chromatograms. What is the x-axis? If you guys take a look over here, you'll see minutes, right? Your x-axis is time in minutes. So go ahead and add this to your x-axes of your chromatograms, help you more easily understand them. What do you guys think the y-axis is for your chromatograms? Well, again, take a look at the units here. You'll see A, which stands for absorbance. Go ahead and write absorbance. Absorbance, of course, has no units. Another thing that you guys should look at, what wavelength are we using to measure absorbance? You guys remember when we did spectroscopy earlier, how we had to select a certain wavelength to be able to measure our red dye solutions. The wavelength we're using here is 280 nanometers. And that wasn't just something selected arbitrarily. That was something Dr. Cory measured over time. She was looking for a wavelength that aspirin, acetaminophen, and caffeine all absorbed at, and that just happened to be one of them. So go ahead and circle 280 nanometers on all your chromatograms. You'll also notice on your chromatograms that there's a little tiny bump here right before your giant peak. That's called the solvent front. It's a feature in every chromatogram. That's because when the HPLC is trying to inject your sample onto the chromatogram, it also injects 20 microliters of water through the column to kind of push out the previous sample and some solvent that's sitting in there. It kind of separates and gets you ready on your chromatogram for your actual peak of your sample. We zero the UV spectrometer to solvent, so when it sees water, which is not your solvent, it's going to register an absorbance. So go ahead and just label those solvent front on all your chromatograms, just so you understand. So before we start talking about our unknown, each standard chromatogram should have a solvent front and one peak. That one peak corresponds to your sample. If you have more than one peak, we need to talk about contamination. We'll also talk a little bit about that as we move on. Your unknown chromatogram is going to have multiple peaks. If you guys remember, your unknown is Goody's headache powder. Goody's headache powder has 3 medications that makes up the combination, so it should have 3 peaks. We'll talk about that as well. We'll start first with acetaminophen. Acetaminophen is very polar, as we spoke of, or as we will speak of, I'm sorry, a little bit later. It comes off the column at 2.1 to 2.6 minutes. You guys should see that on your standard chromatogram, and then you should also see it on your unknown as well. This number that sits above the peak is your retention time. I'll show you why that's important here in a second. Go ahead and round that to 2 significant figures, and then write minutes next to that as well. That'll help us to identify it when we're looking at peak areas later on. Here's the caffeine. It comes off about 2.8 to 3.7 minutes. Go ahead and round that number as well and write that next to the peak. And then go ahead and take a look at aspirin. This one comes off a little bit longer from the column, between 4.5 and 5.7 minutes. Excuse me. And that is because it is very nonpolar. Go ahead and do the same thing here. Circle the retention time and round your minutes to 2 significant figures. We're going to talk about this little peak here in a second. That's a contamination from aspirin. So, talking about polarity. Based on what we know from the column, we can estimate the polarity of each of our compounds. You can tell a little bit by looking at them, but it's very difficult. It takes some experience to be able to do that. So based on our chromatogram, you'll note that acetaminophen came off the fastest, meaning that it is gave away one of the answers there. Aspirin is the most polar, whereas I may have made a mistake there. Acetaminophen is the most polar because it came off the column the fastest. Aspirin, however, took the longest to come off the column, meaning it is the most nonpolar. So the most polar of the three, acetaminophen. The most nonpolar of the three, aspirin. And then caffeine falls somewhere in between. For you chemists out there, acetaminophen is the most polar because it does have these hydrogens here. Those are going to participate in hydrogen bonding, the oxygen here as well. Aspirin, it does have this hydrogen, but it is protected by this group over here. Not a lot of bonding is going to be going on. Caffeine, these oxygens might participate a little bit, but you can tell polarity just based on acetaminophen. When I was working in a compounding pharmacy, we would be brought these drugs, mostly like veterinary medications, and people would ask us to put it into a solution because they couldn't give their dog a tablet for whatever reason. So I would look up the structure of the medication, and just based on these hydrogens as well as any sort of oxygen groups like this, I could tell, I could better guess at what the polarity was, and that helped me to determine whether or not to break down the drug and put it into either water or oil for the dog to take based on its polarity. Let's talk a little bit about contamination. The first one we're going to talk about has to do with aspirin. As you can see with aspirin, it's coming off usually between these times. This one came off a little bit sooner. This tiny peak over here actually correlates well to salicylic acid. Salicylic acid is a degradation product of aspirin. When aspirin interacts with water, the water cleaves this bond right here, leaving us with salicylic acid and acetic acid. This is what's happening in your stomachs when you take aspirin. When I talked to you guys the other day, and when I made a post in Oaks talking about degradation does not equal a loss of potency, this is a primary example here. Aspirin is the active ingredient. Aspirin does interact with the COX-1 and 2 receptors, which do have an effect on platelet aggregation, as well as inflammation and the such. You guys probably have learned by now that aspirin is similar to ibuprofen in having the same effects. I bring this up because although salicylic acid is a degradation product of aspirin, salicylic acid does maintain activity at the receptors and is still an active ingredient. It is still an active medication. It shows potency. So even though aspirin is degrading, it is not losing potency. Salicylic acid is still potent. So unless you guys want to work with the IRB to have a clinical trial with your Benadryl tablets, your degraded Benadryl tablets, I shouldn't be seeing anything about loss of potency on your reports. Some of the other contaminations you'll see happen around the peaks with acetaminophen and aspirin. Here are some examples here. They're kind of tiny. That looks like a solvent front, but definitely over here you'll see this aspirin has this weird peak at the beginning. These happen because of contamination, and we will definitely not be using those to calculate anything, although we will be mentioning them in our discussion as potential sources of error. Go ahead and circle those. In this case, in this acetaminophen chromatogram, it looks like this peak correlates well with where caffeine would come off on the chromatogram. So maybe the person who was measuring out their acetaminophen also used the same spoon to measure out the caffeine earlier, and that's why they have a little bit of caffeine in their acetaminophen sample. And the same thing with their aspirin over here. They've got some salicylic acid, but they also have some caffeine contamination. Where do these contaminations come from? I just mentioned one earlier. Salicylic acid, can't do anything about it. When aspirin interacts with water, it's going to form salicylic acid. We just have to work quickly to make those samples, but we can't prevent it. If you guys didn't rinse your volumetric flasks, you really did take a leap of faith in trusting the people that have used those volumetric flasks before you. They may have used it for a totally different sample. You might have put your acetaminophen sample in their caffeine sample. And of course, you're going to get some contamination. So, of course, we're all going to see some contamination. It's just how much are we going to see. And then, like I mentioned earlier, a dirty microspatula. Say you use the same microspatula to measure all your samples. Of course, you're going to see some contamination. So some contamination, like the salicylic acid, can't really do anything about. But you absolutely can do something about and must do something about contamination in your other samples. So make sure you're rinsing out all your glassware. Rinse it more than once to be certain. I know I'm saying this after you guys have already made your samples with your Benadryl, but just for any further lab work that you do, this will be very important to know. And then your microspatula. It's not a nice thing to say, but you can't really trust your lab mates to be keeping everything clean. So trust but verify. Go ahead and clean that spatula yourself. Make sure that it's clean before you weigh something out. And same thing with your volumetric flasks. Make sure you're cleaning those too. And your pipettes. And then always make sure that you're rinsing out your pipettes with the solution that you're measuring before you use it. Make sure you prime those pipettes. Let's go ahead and get started on talking about some of the math that goes on into calculating the amount of drug in our headache powder. So in this example here, this is aspirin, comes off at 4.6 minutes. We've labeled our salicylic acid. I can use this value here to go to the bottom of the table and find this retention time in minutes here, and then I can use that to find its peak area. So go ahead and circle these values for each of your standard chromatograms, and then the other values that correlate with other peaks, I don't really care about those. Just circle the ones that matter for, in this case, aspirin, and then acetaminophen and caffeine as well. So this is pretty important. HPLC tells us two things. It tells me what the compound is based on its retention time. I know that this is aspirin because it comes off the column at about 4.6 minutes. I can tell the same thing about caffeine and acetaminophen based on where they come off the column. That's why you guys will be able to label the peaks on your unknown chromatogram because you know where they come off based on your standard chromatograms. The second thing that HPLC tells us is how much of the compound you put through the column. We can calculate that based on peak area. Speaking of, this is how we do those calculations. So your lab manual has a pretty good step-by-step process, but I'll explain it here myself. And of course, you guys are welcome to email me with any questions you might have. If we need to, I can always set up an in-person meeting with you guys too, and we can try to work out these problems together as well. So if you guys wanted to calculate the concentration of aspirin in your unknown, I would take the peak area of the aspirin in your unknown, multiply it by the concentration of aspirin that you should know because you measured it out before you made your standard, divided by the peak aspirin of the peak area of your aspirin in your standard. Again, this value comes from your unknown chromatogram. This value is something you should know, should be written in your lab notebook. And then this value comes from your aspirin standard chromatogram. This value isn't much use to us when we're calculating further values later on, so we need to convert it to milligrams. We do that by taking that value right here, multiplying it by the molar mass of aspirin. That's something you should have written down in your lab notebook from when we had it on the board a few weeks ago. Convert it from grams to milligrams. Nice, thank you. And then also multiply it by the dilution factor. In this case, it's 10 liters. And this is how we calculated that. So, why is that important? Why do I need to know how many milligrams of aspirin, in this case, is in my unknown? It's because we need to calculate something called percent label claim. The makers of Goody's headache powder are required by the FDA to have a amount of aspirin listed on their box, and they are required to have that amount, at least 80 to 120% of that amount, within that medication. So, go ahead and calculate the actual milligrams for caffeine, acetaminophen, and aspirin according to these calculations here. And then what you're going to do is use the box label claim, which conveniently I've put right here for you. These are the ones that Goody's claims is inside each one of their little powder packets. So we'll divide our milligrams from the HPLC chromatogram by each one of these values. Convert that decimal to a percent, and that's your percent label claim. That should fall between 80 and 120%. If it falls outside this range, either we have some bad Goody's powder or your calculations didn't work out too well. Again, I'll leave this up for you guys just to reference. Go ahead and pause the video here. I know I mentioned it in class, but I know some other students will use this video. Goody's powder is not good for headaches. In my opinion, and in many pharmacists' opinion, it's addicting, one, because over time it does lose its effect. There are several people that I know of that just, have a lot of Goody's powder. It's potentially dangerous to children and teenagers who use Goody's powder because it does have aspirin in it. It can cause something called Ray's syndrome, which is a virus that attacks your liver. It can be potentially fatal. But if you guys do have headaches, I recommend acetaminophen or Tylenol. That's always very effective. But then also, all three of these ingredients are included in a medication called Excedrin. That one works pretty well for me. It's got some safer quantities, in my opinion, and that way you don't have to, eat a powder packet either. For my class, because you guys don't want to meet on that Saturday to make up the lab, go ahead and complete the Week 7 lab report sheet. That's found on pages 82 to 85. Go ahead and complete that and turn it in at the beginning of lab next week. I know it's a lot of extra work on top of the methods that you guys have to type up, but that will save us from having to come into lab on a Saturday night from 7 to 10. I hope you guys enjoyed this video. I know it's a little bit long, but this lab was supposed to be pretty long. This is going to be super helpful for us when we start talking about how to interpret our Benadryl HPLC results next week. So go ahead and get started on this. email me if you have any questions at all. If you guys are like really confused, we can talk about meeting up for some office hours and talking about it more in person. Thank you guys for listening. I appreciate it. I'll see you guys in class on Thursday.